All right, this is the gravitational potential energy argument. So in this argument, we're going to be starting with a very basic principle from physics about gravitational potential energy. Draw again the surface of the Earth, represented by this green line here. Now we all know that Earth has a gravitational field. The amount of energy that the rock has at this location is called gravitational potential energy. And the gravitational potential energy at a height h of something with mass m, this gravitational potential energy is just the mass of the object times the height that it is dropped times the gravitational field. So what's this have to do with New Jerusalem? Most people have interpreted Revelation as saying that New Jerusalem will come down and land on Earth. However, there is a huge problem with that. And the huge problem presented in this argument is the gravitational potential energy. Okay, so here's a depiction of New Jerusalem. The length of its sides is 2,200 kilometers. And the radius of Earth is about 6,370 kilometers. For New Jerusalem, we have to use a more complicated formula for calculating the gravitational potential energy because the strength of the Earth's gravitational field does significantly change at these distances because New Jerusalem can't just be close to the surface of the Earth. So for that situation, instead of just calculating it based on how far away it is, formula for calculating the gravitational potential energy, usually specified with U, is the negative of the gravitational constant times the mass of the first body, so that's mass of the Earth, times the mass of New Jerusalem, so that's the mass of the second body, divided by R, where R is the distance between the center of each object. So R would be the distance all the way from the center of New Jerusalem to the center of the Earth. And when we want to calculate what the change in gravitational potential energy would be if New Jerusalem were to land on Earth, we have to start by assuming that it's a certain distance away, distance of 2 radiuses of Earth. We could then calculate how much gravitational potential energy it would have if it were to come and land on Earth. So we can calculate all of that. We can make assumptions to calculate R. The mass of the Earth is known. I'll just write it here. And the gravitational constant is also known. It's about 6.7 times 10 to the negative 11. And the mass of the Earth, 6 times 10 to the 24 kilograms. And we already specified the radius of the Earth here. And so if we're going to calculate the gravitational potential energy, all we need is to know the mass of New Jerusalem. And in order to get that for this, we just need to make some basic assumptions because it doesn't specify exactly what the mass is. But it does specify how long the sides are, so we can calculate the volume. So the volume of New Jerusalem is quite easy to calculate. It's just 2,200 kilometers cubed. So in order to get a mass for New Jerusalem, we just need to make an assumption about its density. For this assumption, I propose that we just kind of assume that it's about the same density as water, because we know that New Jerusalem is made up of exotic materials like gold and jasper, but we also know it's hollow on the inside, so it's got some heavy elements, some metals, but it's also hollow on the inside, so it should mostly also be filled with gas. So let's just assume it's about as dense as a boat, or about half the density of water. The density of New Jerusalem is about 1/2 gram per milliliter, which is the density of water, which is 1/2 the density of water, which is about 500 kilograms per meter cubed. So we're going to translate all these units into kilograms and meters, and then we can calculate the mass of New Jerusalem as being the density times the volume. And we have the volume here, we have the density here. That's an assumption. To get an estimate for the order of magnitude for how much mass are we talking about here for an object that's of this size. We just calculate that out. Mass of New Jerusalem is about, and then we need to convert kilometers cubed to meters cubed. It's about 5.3, 10 to the 3, 10 to the 9, times 10 to the 9. So that's 5.3 times 10 to the 18, 21. The mass of New Jerusalem with this density as an assumption is about 1,000 times smaller than the mass of the Earth. Mass of New Jerusalem is about 5.3 times 10 to the 21. And now we have everything we need to get an estimate for the gravitational potential energy released as a function of New Jerusalem landing on Earth. So how much energy are we talking about here? So let's assume that we're calculating basically the energy of it going from a radius of about 2 radiuses of Earth to 1 radius of the Earth. The change in energy is going to be equal to G times the mass of the Earth times the mass of New Jerusalem, 1 over our Earth minus 1 over 2 radiuses of the Earth. So that's just assuming that New Jerusalem is starting 6.4 thousand kilometers away from the surface of the Earth. So this is also another assumption that we're making just to get a rough order of magnitude for what kind of energy we're talking about. Okay, so we have everything that we need to calculate an estimate for how much potential energy would be released if New Jerusalem were to land on planet Earth. And before we actually calculate this value, let me put some context to the number. So during the Cold War, the largest nuclear weapon ever tested was the Tsar Bomb by the Soviet Union. And that bomb released an energy of about 2.1 times 10 to the 17 joules. Let's keep that number in mind while we calculate this. So, plugging all these numbers together, the total energy change we're looking at is about G times ME times MNJ. That is about 2.1. Adding all these exponents here, we get 2 minus 11 plus 24 plus 21, and then divided by the radius of the Earth. And we want to translate this radius of the Earth into meters, about 6.4, 10 to the 6 meters. And then meters squared, kilograms per second squared, that's a unit of energy, that's joules. Calculate that out, and we get, so that is 1.6 times 10 to the 29 joules. Now let's compare that to the amount of energy released by the Tsar Bomb, about 2.1 times 10 to the 17 joules. You see the problem here? Look at the energy released by New Jerusalem landing on planet Earth. It's an absolutely massive amount of energy. That much energy, that's the size of the explosion, the devastation that would be released upon the Earth and upon New Jerusalem if you tried to land New Jerusalem on planet Earth. That's the end of the argument. It's too much energy. It would be a catastrophic failure. It would destroy the Earth, it would destroy New Jerusalem. Therefore, New Jerusalem cannot land on Earth. If it cannot land on Earth, it therefore remains in space. If it remains in space, it is therefore a spaceship.